Okay, in this lecture we're going to continue our work through section 3.5 on the method of undetermined coefficients. And before we look at some examples, let's recall how this method of undetermined coefficients works. So as a reminder, to find the general solution of the non-homogeneous equation, shown here, we first find the general solution, which would have the form C1y1 plus C2y2 of the corresponding homogeneous equation. And we call this solution the homogeneous or complementary solution, and it is denoted by y sub h of t or y sub c of t for homogeneous or complementary solution. And then our second step is to find some solution, capital Y of t, of the non-homogeneous equation. And this solution is usually called a particular solution and denoted by either y subscript p of t or capital Y of t. And in order to find one particular solution of the non-homogeneous equation, we usually have to make some initial assumption about the form of our particular solution. So this method of undetermined coefficients requires us to make an assumption about the form of this particular solution or some initial guess about the form of that solution. And in this lecture, we'll see some examples on how to construct that form for the particular solution. And then once we have found our homogeneous and particular solutions, the general solution of the non-homogeneous equation is the sum of our homogeneous and particular solutions. So in summary, again, to solve a non-homogeneous equation, we first solve the corresponding homogeneous equation. We then find some particular solution of the non-homogeneous equation by guessing or making an assumption about the form of that particular solution. And then once we have our homogeneous and particular solutions, the general solution is the sum of those two. So let's consider some examples of this process. In this first example, we are asked to find the general solution of this second-order linear non-homogeneous equation. We see that it is non-homogeneous because we have this g of t function on the right-hand side. Here our g of t is 12t. And we are going to first solve the corresponding homogeneous equation. So let's consider it. We start by considering the homogeneous equation, y double prime plus 3y prime plus 2y equals 0. And to solve this type of equation, we could look for solutions of the form y equals e to the rt power, which means that r would have to be a root of the characteristic equation, r squared plus 3r plus 2 equals 0. And this can be factored as r plus 1 times r plus 2 equals 0. Which means that r could be either -1 or -2. We're working with the case of distinct real roots for our characteristic equation. So the general solution of the homogeneous equation, which we call the homogeneous solution, and we denote it as y subscript h of t, would have the form c1 e to the -1t plus c2 times e to the -2t. So this is our first step. We find the solution of the corresponding homogeneous equation. And now we need to find some particular solution of the non-homogeneous equation. And this method of undetermined coefficients requires us to guess the form of our particular solution. Now, how do we guess the form of our particular solution? Well, we're going to look at the form of the g of t function on the right-hand side. Here, g of t was 12 times t, which is a first degree or linear polynomial. So let me write here, this is a first degree polynomial, or a linear polynomial. So let's try guessing a particular solution, or let us consider a particular solution that would have that same general form. So here I'm going to use capital Y to denote my particular solution. Some people prefer Y subscript P of T. Either one that you prefer to use is fine. And here let's consider a general first degree polynomial, something of the form AT plus B, where these coefficients, A and B, are unknown constants that we need to find. So hence the name undetermined coefficients. We need to determine what these coefficients A and B are, which would make this function a solution of our non-homogeneous equation. So to find our coefficients, we're going to substitute capital Y and its derivatives into our non-homogeneous equation. So let's find our derivatives. Capital Y prime would just be A, and capital Y double prime would then be 0. And so substituting into our non-homogeneous equation, we would be looking for y double prime plus 3y prime plus 2y. And we need this to equal 12 times t to give me a solution. So substituting these expressions in, well, our second derivative, y double prime, was 0. We then have 3 times y prime, which was a, plus 2 times y, which was at plus b. I need this to equal 12t. So if I expand on the left-hand side and group like terms, I have a 2a times t. And then grouping my constants together, I have a 3a plus 2 times b. And I need this to equal 12t. So in order for this equation to be satisfied, well, our coefficients on the left and right hand sides have to be equal to one another. So if I equate these coefficients of t, I see that 2a has to equal 12, and so a would then have to be 6. And then equating my constant coefficients, this 3a plus 2b, would have to equal 0, since I didn't have a constant term on that right-hand side. So we find that 3a plus 2b has to be 0. So 2b would be negative 3a. And since a was equal to 6, we have 2b is negative 18, and therefore b would be negative 9. So once I have my coefficients a and b, we have found our particular solution, capital Y. capital Y was given by A, which was 6 times t, plus B, which we found to be negative 9. So capital Y, which would be 6t minus 9, gives me my my particular solution of the non-homogeneous equation. And so to find our general solution, y of t of the non-homogeneous equation, we sum the homogeneous solution, which was c1 e to the negative t plus c2 e to the negative 2t, and our particular solution, which was 6t minus 9. Okay. Now, one thing that I'll try to stress as we work through these examples would be how to handle some different cases for this g of t function. So as we've seen in this first example, if g of t is a linear or first-degree polynomial, we would look for a particular solution of the same form. Now let's say that we changed this slightly. So a little scratch work here. Let's say that we had made g of t, the function on the right-hand side, 12t squared instead of just 12t. So here we would have a quadratic or a second-degree polynomial. And so we would consider a particular solution, capital Y, of the same general form. So a general quadratic would be something of the form at squared plus bt plus c, where we would have to solve for a, b, and c in the same way that we solved for a and b in this example. So in general, if g of t is a nth degree polynomial, we would consider a particular solution of the same form, a general nth degree polynomial. So let's look at another example. In this next example, we have the same sort of problem as in the last one. We're asked to find the general solution of this second-order linear non-homogeneous equation. And so we know that our first step is to solve the corresponding homogeneous equation. So let us start there. We will consider the equation y double prime minus y prime minus 2y equals 0, which we can solve by looking for solutions of the form y equals e to the rt power, which means that r would have to be a root of the characteristic equation, r squared minus r minus 2 equals 0, which can be factored as r plus 1 times r minus 2 is equal to 0. And so r would be negative 1 or positive 2. Again, we're working in the case of distinct real roots of that characteristic equation. So our homogeneous solution, y sub h of t, will have the form c1 e to the negative t plus c2 e to the 2t. So our next step is to find some particular solution of the non-homogeneous equation, and this method of undetermined coefficients requires us to make some assumption or guess about the form of our particular solution. So to determine the form of our particular solution, again, we will look at this g of t function on our right-hand side. G of t is 20e to the 3t. And so here we have a constant times some exponential. So let's consider a particular solution of the same general form. That is a particular solution, capital Y of t, given by some constant, let's call it a, times the same exponential, e to the 3t. And we need to determine this coefficient a that will make this a solution of our non-homogeneous equation. So we're going to substitute this function and its derivatives into our non-homogeneous equation. And let's start by finding our derivatives. Y prime would be given by 3a e to the 3t. And our second derivative, y double prime, would be 9a e to the 3t. So substituting into our non-homogeneous equation, we're looking for capital Y double prime minus y prime minus 2y, and we need this to equal 20e to the 3t to give me a solution of my non-homogeneous equation. So let's substitute in. We have y double prime was 9a e to the 3t minus y prime, which was 3a e to the 3t, minus 2 times y, which was a e to the 3t, and I need this to equal 20 e to the 3t. So collecting my terms on the left-hand side, I'm left with a 4a e to the 3t, which has to equal 20 e to the 3t. And so equating these coefficients of my exponential function, we see that 4a would have to equal 20, and so a would be 5. So substituting this value back into our particular solution, we find a particular solution, capital Y, would be a, or 5, e to the 3t power. And then to find our general solution of this non-homogeneous equation, we would take the sum of our homogeneous solution, which was c1 e to the negative t, plus c2 e to the negative 2t, e to the positive 2t, and our particular solution, which was 5e to the 3t. So here we were working with a g of t function, which had the form a constant times this exponential. So we looked for a particular solution of the same general form, a constant times the same exponential function. Now let's say that we changed this slightly. So considering a slightly different g of t function, let's say that g of t was of the form 20 times t e to the 3t. That is a linear function times an exponential. So in that case, we would look for a particular solution that would have the same form, some general linear polynomial, at plus b, times the same exponential function. Similarly, if we had a quadratic times an exponential, we would consider a particular solution that would be a general quadratic times that same exponential function. So let's look at some other ones. In this next example, we'll see a case where our initial assumption about the form of the particular solution may not work out correctly, and we might have to modify our initial guess about the form of the particular solution. Here we are asked to find the general solution of the second-order linear non-homogeneous equation. And our first step is to solve the corresponding homogeneous equation, which would be y double prime plus 2y prime plus 5y equals 0. So to solve this homogeneous equation, we would look for solutions of the form y equals e to the rt power, which means that r would be a solution of the characteristic equation r squared plus 2r plus 5 equals 0. And this one doesn't factor nicely, so we could solve for r using the quadratic equation, where r would be given by -2 plus or minus the square root of 2 squared minus 4 times 1 times 5 all over 2 times 1. So this gives us a -2 plus or minus the square root of -16, which would be 4i all over 2. And so we have a -1 plus or minus 2i. So here we're working with the case of complex conjugate roots of our characteristic equation, which means that our general solution of the homogeneous equation, that is our homogeneous solution, would be of the form c1 e to the -t cosine of 2t plus c2 e to the -t sine of 2t. Now our next step is to find some particular solution of the non-homogeneous equation, and we need to make an assumption about the form of our particular solution, which we've been doing by looking at the form of our g of t function on the right-hand side. Here, g of t is 3 times sine of 2t. So, speaking in general, we have a constant times our sine function. So let us consider a particular solution, capital Y, of the same general form, some constant a times the sine function. And let's see what happens. It turns out that this form will not work, but let's see why. If we look at our first derivative, y prime of t, we would have a 2a cosine of 2t, and our second derivative, y double prime, would be -4a sine of 2t. So when we substitute into our non-homogeneous equation, we're looking for y double prime plus 2y prime plus 5y. And we need this to equal 3 sine of 2t. So when we substitute our expressions in, we had a second derivative of -4a sine of 2t plus 2 times y prime would give us 4a cosine of 2t, and then plus a 5 times y, which was a sine of 2t. and I need this to equal 3 sine of 2t. So if I collect all of my sine terms on the left-hand side, I'm left with a times sine of 2t, plus if I group my cosine terms, I have 4a cosine of 2t, and I need this to equal 3 sine of 2t. So if I equate my sine coefficients, I find that a would have to be 3. However, if a is equal to 3, then we have a factor of 12 cosine of 2t, but there is no cosine term on the right-hand side. So if we were to equate the cosine terms on both sides, we would find that a would have to be 0, but a has to be 3 to match the sine terms. So we find that our initial guess for the form of the particular solution doesn't work out here. And the reason is, when we find the first derivative of our sine function, it involves a cosine, and we don't see the cosine terms match up. So let's go back to our assumption about the form of the particular solution. If we go back to the form of the particular solution where we had a constant times sine of 2t, well, we need our cosine terms to work out so that they can cancel one another. So let's also include a constant, let's call it b, times the cosine of 2t. So then our first derivative would be 2a cosine of 2t minus 2b sine of 2t. And our second derivative would be the negative 4a sine of 2t minus 4b cosine of 2t. And so now, if we substitute these expressions into our non-homogeneous equation, let's see what we have. So when I substitute in, if I collect all of my sine terms, let's see what we're going to have. So looking at the sine terms from y prime, and y double prime, when we substitute these in on the left-hand side, our y double prime plus 5y will leave us with 1a sine of 2t. And then the first derivative term, 2 times y prime, will give us a negative 4b sine of 2t. So collecting those terms, we have a minus 4b times sine. And then collecting the cosine terms, let's see what we have. So when I have my first derivative term, 5y, plus the y double prime, I will be left with a b times cosine of 2t. And then from the first derivative term, 2 times y prime, I get a 4a cosine of 2t. So altogether, 4a plus b times cosine of 2t. And this needs to equal 3 sine of 2t. So equating the sine and cosine coefficients, we find a minus 4b needs to equal to 3. And then equating the cosine terms, we find that 4a plus b must be 0 since we didn't have a cosine term on the right-hand side. So here, to solve this system of equations for a and b, well, I could maybe first solve for b in terms of a. B would have to be negative 4a. And then substituting this into my first equation, we find that a minus 4 times b, which would give me a total of 17a, has to equal 3. And so a is 3 over 17. And then substituting this into our b expression, we have b is equal to negative 4 times a, so negative 12 over 17. And therefore, our particular solution, capital Y of t, is given by a, which was 3/17 sine of 2t, plus b, which was negative 12/17 cosine of 2t. And then to get our general solution of the non-homogeneous equation, we take the sum of our homogeneous solution, c1 e to the negative t cosine of 2t, plus c2 e to the negative t sine of 2t. And then we add our particular solution, which was 3/17 sine of 2t minus 12/17 cosine of 2t. So here we have an example where our g of t function involved a sine, and since the derivative of the sine function involves a cosine function, we have a particular solution where we needed to consider both sine and cosine terms. So if our g of t function involves either a sine or a cosine, then we have to include both terms as part of our particular solution. Now let's look at one other example where the initial guess for the form of our particular solution may not be correct. We might have to go back and modify it. Here we are asked again to find the general solution of this second-order linear non-homogeneous equation. And so we know our first step is to solve the corresponding homogeneous equation. So let us consider y double prime minus 3y prime minus 4y is equal to 0, which we would solve by looking for solutions of the form y equals e to the rt, so that r would be a root of the characteristic equation r squared minus 3r minus 4 equals 0. And this can be factored as r plus 1 times r minus 4, which means that r is negative 1 or positive 4. We again have the case of real distinct roots of this characteristic equation. So our homogeneous solution, y sub h of t, would have the form c1 e to the negative t plus c2 e to the 4t. Now our next step is to find some particular solution, so we need to guess the form of this particular solution. And again, to guess the form, we're going to look at the form of our g of t function, which is 2e to the negative t, that is a constant, times my exponential, e to the negative t. So let us consider a particular solution of that same form. That is a constant times the same exponential, e to the negative t. And we'll see that this general form will not work. Let's go through the work of showing that this cannot solve the non-homogeneous equation and explore how to correct this. If we were to find our first derivative, we would have a negative a e to the negative t, and our second derivative would be a positive a e to the negative t. So substituting these expressions into the non-homogeneous equation, we would be looking for y double prime minus 3y prime minus 4y. And we need this to equal 2e to the negative t. So substituting our expressions into the left-hand side, we have a e to the negative t. For negative 3y prime, we get a positive 3a e to the negative t, and then minus 4 times y, which was a e to the negative t. We still need that to equal 2e to the negative t. But when I sum these terms on the left-hand side, I get 0, which is certainly not equal to 2e to the negative t. So there must be something wrong with the form of our particular solution. And the problem here, if we go back and look at this, is that our particular solution was a constant multiple of e to the negative t. However, a constant multiple of e to the negative t was a solution of the homogeneous equation. So here we had a solution of the homogeneous equation, which was a constant times e to the negative t. So a function of that form cannot possibly solve the non-homogeneous equation. It was already a solution of the homogeneous equation. So what form should we consider for our particular solution? Well, let's go back and explore this. Since our initial guess was incorrect and was part of the solution of our homogeneous equation, let's consider a particular solution of a different form. So like we saw in the case of repeated roots of the characteristic equation, we might consider, instead of just e to the negative t, something like t e to the negative t power. So let's look at a constant times t e to the negative t, since just a constant multiple of e to the negative t was part of our homogeneous solution. So in this case, our first derivative, y prime, would be given by using the product and chain rules, a e to the negative t minus a times t e to the negative t. Or if we factor out an exponential, we have a minus a t e to the negative t power. And so our second derivative, y double prime, again using the product and chain rules, would be negative a e to the negative t plus a negative a plus a t e to the negative t. Or if I factor out my exponential, I would have at minus 2a e to the negative t. And now let's substitute into our non-homogeneous equation. We're looking for y double prime minus 3y prime minus 4y, and we need this to equal 2e to the negative t. So substituting in for y double prime, we had at minus 2a e to the negative t. For negative 3 times y prime, we get a negative 3a plus 3at times e to the negative t. And then minus 4 times y, which was at e to the negative t, which I need to equal 2e to the negative t. So if I expand and collect like terms, let's see what we have. Grouping all of the terms involving t times e to the negative t, we see that we would have 4at e to the negative t minus 4at e to the negative t. So these terms will all cancel. And then grouping the terms just involving e to the negative t, we see that we get a total of negative 5a e to the negative t, which needs to equal 2e to the negative t. And so negative 5a would have to equal 2, so that a would be a negative 2/5. So once I find this coefficient a, I can substitute back into my general form for the particular solution. And we find that a particular solution would be negative 2/5 t e to the negative t power. So again, once I find my homogeneous and particular solutions, we find that the general solution would be given by the sum of the homogeneous solution, c1 e to the negative t, plus c2 e to the 4t, and our particular solution, which was negative 2/5 t e to the negative t. So again, in this example, we see a case where our initial guess for the form of the particular solution didn't work out, and we had to modify that initial guess.